Okay, well, welcome everyone to the panel discussion. My name is Jason Alicea. I'll be the moderator. I'm a professor here at Caltech. Let me start by just introducing our panelists. So starting from that side, we have Allan MacDonald from UT Austin, Zhi-Xun from Caltech, Jochen Mannhart from Max Planck in Stuttgart, Zhi-Xun from Stanford, and Charlie Marcus from, actually, I don't know where you work. Are you, do you work at Microsoft or Copenhagen?
I work in Copenhagen.
Copenhagen, from Copenhagen. All right, so to kick things off, I thought we would just go down the line, asking each of our panelists to spend a few minutes describing some key open questions from their respective research areas, and hopefully, as this goes, this can naturally evolve into a discussion amongst everyone here, because we're lucky not only to have a distinguished group of panelists, but also a very distinguished audience. So I hope this can turn into a conversation involving everybody. Okay, so let's begin arbitrarily on this side. Do you want to kick us off, Charlie?
Shoot, I was hoping somebody else would think of what we could talk about.
You can't escape.
Okay, so the question that I've been asked is, what are some open questions in my own field of research? Was that a fair summary of it? Broadly defined. Okay, it's pretty broad already. My field of research is condensed matter experimental physics with an eye on quantum information and qubits. And I think that where we stand in this Majorana world of topological quantum states and topological quantum information is a good metaphor for a lot of other problems, which is that there are people in the community, particularly and especially journalists, but also some scientists, who ask questions like, have you proved it's a Majorana yet? And to me, that formulation of the question proves that they're not experimental scientists, or maybe even scientists at all, because the notion of doing the experiment that proves that something is something, in other words, the arrow points from experimental data to theory, and says that this is the only theory that can explain the data, is generally foolishness. So what we do in the lab is a series of progressively harder and harder experiments, and hopefully a series of more and more refined experiments that rule out alternatives as they come up. And the question of the qubit business, I think, has a dual purpose. One is, especially now, and it's maybe an interesting topic for conversation, have this affiliation with Microsoft, who's genuinely interested in building quantum computing as a technology for computation. But there's this other aspect of qubits, which is that they're a probe of this non-abelian or topological states of matter. And the question that I think I'd like to bring to this audience or to this group of people is, surely one does not need to build an entire quantum computer to establish the emergent non-abelian character of these particles. So what are the easiest experiments that one can do in which it becomes very difficult to escape from the conclusion that nature has hidden in these either complex materials or hybrid materials, non-abelian excitations? Maybe the answer is qubits. Maybe qubits are the answer to the question of what's the experiment that finally convinces you that you've braided particles, or excitations, and that they have this non-abelian character. From my own perspective, that's the interesting question. So qubits then become an experimental tool to test physical states rather than simply something that we use to either build a technology or to get funding. Maybe I'll stop there.
Very good. So I would invite comments or questions from people as we go. Anyone have any thoughts they want to offer?
Does anyone want to say what the easiest experiment to do that would have the nearly inescapable conclusion that non-abelian excitations are indeed non-abelian?
No, I didn't want to answer that question.
Oh, if you want to have another one, okay.
Please, yeah.
So you're putting all the responsibility on the theorists.
Not at all.
What are the experimental innovations that you're working towards to make it easier to do experiments that can make it very hard to
Et cetera,
come up
yeah.
with other
I think I can answer that, and I think it's an interesting answer that I have, because I missed some of the morning talks. I apologize, Duncan, I was on my way down here. But boy, I heard the word materials a lot during the last two talks, and I think that I want to just re-emphasize that it's a material world, and I'm a material guy. I think that the particular answer is that a lot of this non-abelian business arose, in my lab anyway, arose from ideas that I believe are traceable back to Alexei Kitaev, although maybe Alexei will tell us that they're actually traceable back to in my head, they're traceable back to Alexei Kitaev. And so we spent a lot of time working with one-dimensional nanowires, which are a fantastic material science accomplishment, but in some ways are really no way to run a business, because they're hard to work with, they're bottom-up assembled things. And I think that the evolution from epitaxial superconductor semiconductor systems grown in nanowires to two-dimensional systems, and then ultimately to something like selective area growth, where you can make arbitrarily complex networks of webs of wires that move around, it's not an experimentalist accomplishment. I would call it a material scientist accomplishment, but it has greatly simplified and also, let's say, enlivened our imagination for what kind of things we can build with very little difficulty. So I'll say that material science has made the biggest difference.
Yeah, first, I'd like to comment this Majorana excitation, at least in 2D, traceable back to red and green, maybe even back, but I don't know about that. And I have a suggestion about experimental test. I think the best test would be the 4-pi periodic Josephson effect. Of course, in some sense it has been done, but it needs to be demonstrated that is a DC effect, that the system lives in a certain parity state for long enough, and during this lifetime we can observe the 4-pi periodic Josephson effect. I think if this is done, then it will be very hard to come up with an alternative explanation.
Wonderful. Let me draw you a picture of a device. I can either flash it or I can draw it for you on a napkin afterwards. Oh, okay. Yeah. And you tell me whether there's a board, but there's no chalk. It's very clean here. There's not even chalk dust. Suggesting that there hasn't been chalk here for a while. Why should there be erasers? Wait, do you want?
It should be here. It's here. Okay, there are chalks.
Yeah. Okay, good. This is a device that we've made, which is a plus. I mean, we already have it, and it would be interesting to hear if this does make it or not make it as far as the test that you're concerned with. For those people in the audience who live in a world of superconductors, this thing is going to look an awful lot like a DC squid.
It looks like a transparent DC, but you can't see.
Like a what?
Like a transparent DC squid because we cannot see.
Oh, because I'm standing.
No, we can see it.
Oh, it's lousy chalk, you're saying? Oh, well, I'll do my best. These are weak links in the usual sense of a squid, and people who do this thing for a living know that what you do is you apply a flux through here, and that there's very often some kind of response, like the critical current or something like that, which is periodic in the flux divided by the quantum of flux. If one now generalizes this, I think we even have colored chalk here. This box, it seems like it hasn't been opened in a long time. Well, okay. If one now generalizes this to create Majorana fermions here, and I guess, let's say one transitions from a topological superconductor to a trivial superconductor, let's say here as an example, so I'll put a couple more Majoranas there, but they're irrelevant, so I won't scrub them in very hard.
And each pair is connected by a wire.
Yeah, sorry, what I mean to imply is that this solid region here, which maybe I'll use a whole color for that, the solid region here this is trivial superconductor. What I've drawn in stripes is trivial superconductor, and what I'll draw in, I'll make it another color, yellow, with polka dots, is a topological superconductor. Okay, so that's a segment of topological superconductor. And let's say it's one-dimensional, so it's thin. We can do that. So there's Majoranas there and Majoranas there, and this is a weak link, which means that there's a coupling here which has both a Josephson character and a Majorana coupling between those two, and the same thing, of course, here. So let me give them an index 1, call this one 2, and 1. And the flux dependence will have a different periodicity for the Josephson part as for the Majorana part. This will be a 4 pi periodic in units of h over 2e, and this will be 2 pi periodic in units of h over 2e. And so my question to you is, do you need more than that, or is there something missing? This is a DC transport experiment.
No, that would be great, but there are some details. If you do the experiment fast, then you're supposed to see this 4 pi periodic curve if you have cancelled the 2 pi component completely. However, at longer time scales, there will be tunneling between the Majoranas in the contact and there's extra Majoranas.
Yep.
And there will be switching, and eventually you'll switch to the 2 periodic.
If I only have to worry about so-called poisoning, quasi-particle poisoning, yeah, sorry, go ahead.
I'm a bit lost because with conventional superconductors, with high DC superconductors, we made many squids which were 4 pi periodic or even 8 pi periodic, and there's no indication that there are Majoranas present.
Is it AC measurement?
Just so suppression of the 2 pi component. So a non-harmonic IC-phi relationship.
Non-harmonic.
No, that
opposite,
that makes higher harmonics. I think that what Alexei is talking about is a subharmonic.
Yeah, it's a subharmonic.
It has to be half the frequency, and that's tricky to get.
Yeah.
So,
Okay, I
sorry.
actually suggest that
Yeah, well,
maybe
let's go on.
we have very
let's
tight
take this
time.
offline, but this is kind of
That's wonderful.
Yeah. okay. Good.
Okay, so this is something we can continue after. So maybe let's move on to Zhi-X.
That's great. It's always fun to sit next to Charlie. Last time I sit next to him was the evening, late night evening out. Had a movie and a dinner. Next morning, Charlie sent a message saying, the baby arrived. No more late night out.
That was exactly 18 years ago.
Exactly. So for my area of the physics, we're interested in material properties of material physics. Really two things. One is the precision control of material. The other is precision measurement modalities. And we just hear a nice talk on this monolayer system. And in this case, you really have to control the materials to the atomic precision. And you can actually engineer a superconducting properties. Otherwise, you cannot get. That's a good example of precision control of material. And the two talks in the morning has illustrated that very clearly. The heart and soul of what we do really lies on material, and Charlie will agree to that. It's the same thing. Another example of control of material is this new transition metal dichroic carbonides. If you make them a monolayer, you get a electronic structure and beginning to see transport properties, showing that of the quantum spin Hall systems. So again, if you control material, you can create things that's fairly unique. Okay. So that's one aspect of it, and I think for condensed matter physicists, if you have a material, you have a platform, you have a foundation, on top of that, you can do what you want and build many, many things. I mean, one Yayu's talk this morning, once you have a quantum anomalous Hall, you can even build a quantum spin Hall, you can build many other things like Ken Wang have said. The other thing we always know in doing our field is precision measurements. And there are many things of making precision measurements. One of the things we look at it is how you can add a time dimension to the precision measurement. This is one of the recent experiments we've done, try to measure the electron-phonon coupling in a system where you have multiple degrees of freedom. They appear to play on top of each other. Let's say if you want to measure the electron-phonon coupling, you could do that with traditional method by analyzing optical, Raman, various properties, but you always have to assume something, density of states, things like that. Then if you have uncertainty in your assumption, then you have uncertainty in your final result. One way you can do that with the modern time domain experiment, you actually could measure that directly without assumption. And for example, in this case, we are measuring so-called deformation potential. Essentially to say that I'm taking an atom and move the atom slightly up and down, and I see the energy level change, microscopic energy level change of the electrons. And of course, that is the ultimate measurement of the electron-phonon coupling. But on the other hand, it is one of those cases, signal to noise really is very difficult to achieve. That's the signal to noise issue. But with the time domain in this case, what you see here is pump and probe X-ray diffraction intensity of the lattice. Okay, and you can see that at the time delay, you can see that X-ray diffraction intensity oscillates. From that, you can see the tiny amount of motion. Then you use a time-resolved photo machine, try to measure the energy level change. So that's what you see here. The top of the data is a motion of the atoms up and down. That's the critical motion of this particular layer atom, and you can see that. You can see the signal to noise. The full scale is less than 1 picometer, okay? And in a diffraction that gives you that level of sensitivity, then you can also, the two lower curves are the energy level of electrons moving, both of them moving at 5.33 terahertz, and you know they were related to the motion of that. From that, you can say, okay, I know how much my lattice is moved, less than a picometer, and how much my energy level moved. From that, you can verify you are in a linear response regime, and then you can measure the deformation potential. And in this particular case, it turns out there are two theoretical predictions. One is from the density functional theory, that's one value. The other is dynamic mean field theory. In other words, take the density functional theory, add the Coulomb interaction in this case, and they predict a value which is the 1 order magnitude difference for the electron phonon. For those of us interested in this problem of superconductivity, order magnitude difference is a big difference on that parameter. And the experimental result is consistent with the one with strong Coulomb interaction quantitatively, will differ from the density functional theory by order magnitude. So with that sort of precision measurement, you can begin to test theory in complex theoretical systems where there's no consensus on the theoretical model. Therefore, the traditional way of making measurements where you also need some theoretical input, then you sort of become sort of feeding on top of each other, not necessarily self-consistent. So there are many ways of doing that. So again, come back to one is, of course, we really have to push and try to control materials. The second is inventing new modalities to make measurement to a precision that you can really test series and discover discrepancies. When experimental theory has discrepancies, is often when there's opportunity to make advances. Thank you.
Yes, wonderful points. Anyone want to offer comments or questions? Actually, I have a question. Yeah. So I wonder if one can use these precision measurements to provide feedback to, let's say, density functional theory to improve their methods, to be able to, to boost those methods to be able to make more reliable predictions in the future?
That was really our goal, because the prediction was so different. And so what we had hoped now to do is this is just do it in one particular location in the Brownian zone, that we can make the whole momentum space. I mean, we know there are two momentum space. That's a reciprocal space called K, and there's a reciprocal space called Q. They are different. Okay. They connect one to another about interacting systems. This way we can make advances to quantum many-body systems. We all know that precision is really important to have predictive power. When you have some physical properties, once you know the structure, let's say you have a diamond structure, it's very strong. You have strong bond. And some physical properties, like semiconductor band structure, you only really need to know at the bonding level, right? Chemical bond level, electron volts. But if you're interested in the problems right here, or superconductivity, you have to have the energy scales by another 2 to 3 orders of magnitude down, and that precision measurement will become very important. So much of what we do is, of course, many different manifestations of the Schrödinger's equation, and we've been focusing a lot on energy spectrum, right? As you go down to better and better resolution, you go down the energy spectrum. The recent advances of connecting all those topological concepts and ideas to real materials has a lot to do with the wave function, and pay attention to wave function. Then you can also learn a lot of things of that. In the same way, a precision measurement can give to you.
Okay, sounds great. So, yeah, please. Yeah.
What changed and is changing that enables advances in precision measurement?
I guess different technique and the different. If I will look at the photo emission, okay, I would say that it's a combination of all things: detector, spectrometer, the light sources, and most importantly, matching to right experiments.
Okay, and these are kind of commercial or government, or what? I mean, are there new boxes that weren't available before?
There's no turnkey system. Let's look at our own case at the Stanford. We probably from the beginning, when we were together. From now, it's probably 4 to 5 orders of magnitude improvement. I would say is the distributed, the spectrometer, okay, and the beam lines and better materials. When we make the D-wave measurement in 1993, okay, and that's at that time we can make 4 measurements of one fresh prepared surface before the first surface is gone back. So 3 hours per spectrum. And today, in one day you can make 10,000 spectra, 3 seconds or less, with better resolution. And the quantity matters, actually. If you have a map of all those informations, it gives you insights that the individual discrete measurement wouldn't give you, because it will allow you to make connections. Otherwise, you wouldn't do. So I would attribute that to 3 or 4 things, rather. None of that, of course, is simple commercial thing. Only the spectrometer and the detector you could buy components which are specialized, but otherwise, like all experiments, you have to put your own fingerprints on it. Yeah. Good.
Okay, so I should apologize for my poor moderating skills, but we're down to less than 15 minutes until our hard cutoff, and we have 3 people left, so maybe we can, let's say 5 minutes on each of the remaining panelists. So Jochen, do you want to kick us off?
Yeah, so we are building essentially on the science and the applications that has been done with semiconductors 20, 30 years ago. The semiconductors are materials of outstanding purity, and one has atomic control in growing them, in depositing them. And in the meantime, we have learned that there is a whole periodic table and many, many compounds with completely new properties that we can use. And actually, it's also fun because there's just in the universe one periodic table, which we are exploring right now and which we'll be exploring for the next 10 or 20 years. It's a once opportunity for mankind, actually, to do this exploration. And I think this will be a great thing for the years to come. We have learned in advances with the growth techniques to grow many, many different compounds with atomic layer precision. This is just a small sketch of atomically controlled heterostructures that has been done with complex oxides, for example, and related compounds. Now, the next step is actually to use these materials and to pattern them also laterally into quantum structures, which is possible by a variety of techniques, and several groups are working on this. And the most advanced one is Jeremy Levy's group. They have this fancy STM writing techniques, which for some materials they achieve a resolution of very few nanometers. We are doing similar things with e-beam lithography, where we can fabricate quantum devices, for example, for transport, or also quantum dots with a resolution of about 20 nanometers. And this is really exciting, and I think it opens up many perspectives. Here's one example. Strontium ruthenate grown on strontium titanate, a quantum dot. Strontium ruthenate is a ferromagnet. And what you're seeing here is a TM cross-section of a real dot, and the points in the dots are individual atoms. So in this sample, the number of dots on the wafer is larger than the number of atoms in one dot. And it turns out, to my huge surprise, that if one fabricates these dots and one makes them smaller and smaller, you would expect that they deteriorate. But it turns out that the magnetism gets better and better. TC gets higher and higher the smaller it gets. And there is even more possibility. Here is one, the TEM is not as nice yet, where we have the same. However, the quantum dot is just one layer of strontium ruthenate within strontium titanate. So the number of magnetic atoms here, or magnetic unit cells, is just 4,000, which actually puts us into the reach, or getting into the reach, of DFT calculations. So the supercell size and the size of the structures we can fabricate right now starts to overlap. This will be very exciting, because then one can also look into defects and go really ahead. So possibilities, for example, include using these artificial atoms for cold atom experiments. Link them and try to get condensates into these atoms based on this, say, correlated wave functions. And one can think about doing this in a gated way and actually moving these atoms artificially, this fancy ground states, to braiding experiments, or you name it. So I try to come on top of this up with a number of grand challenges, which are actually, I think very exciting, and we are working on it. People are also going into non-equilibrium phases, trying to make new electron systems by exciting them into metastable states. That opens completely new possibilities. One question which I think is super exciting is it possible to make non-dissipative wires, say, that have R equals 0 at room temperature, that are non-superconducting? There is no law that says this is not possible. And I'm actually very positive that this can be done. A very important thing is defects in complex material systems. That is important to understand the materials, and it opens new device possibilities. Nanoionics is fascinating, I think. So building quantum devices where one does not only move the atoms, but also the ions and many different types of ions and reconfigures the devices and makes memories. This goes into neuromorphic devices. We are working a little bit on this, fabricating integrated heterostructures where we actually integrate liquids. Here is one example where we fabricated a wafer where we have 16 field effect transistors, and each field effect transistor has its own liquid gate with a length scale of 10 or 20 micrometers, and they work very nicely. And then I think there's a general trend. In the last 20, 50 years, fabricating transistors and memories has been the top challenge and the most important thing. And I think with the last 10 years, we have realized also that there are quite a number of problems on the planet. I call them here green challenges. You know, green energy, catalysis, water splitting, you name it, where we can make a big impact from solid state science, which will keep us very active. I think they are not academically so deeply exciting on the first sight as fabricating new transistors or qubits, but they are very important, and I think if one starts working on it, the excitement and the academic challenges will come. Thank you.
Okay, wonderful. So those are all very interesting points. I actually have a lot of questions, as I'm sure everybody else does, but in the interest of time, I think we'll hold those and maybe move on to Xia.
Sure. So I am a condensed matter theorist based here. And the area of my study, usually when I introduce myself, I would say a theoretical condensed matter, I work on strongly correlated condensed matter system, or sometimes I would just say it's a strongly interacting quantum many-body system, because the kind of strong correlation, the interaction that we study in some toy models are not at all times well motivated by the ones in a real condensed matter system. But we just use that as an excuse to study in general the whole set of locally interacting models, with the hope that, of course, one day we may get back to real materials, or we may get back to some other experimental system like in cold atom system, where interaction might be more easily manipulated and designed. So I think this is an exciting time for this whole subject, because there's a lot of diversity in the kind of problems, the kind of topics people look at, and diversity in methods that are actually being used. So there are ideas from quantum information, from field theory, or even quantum gravity coming into the study of strongly correlated systems, and people use the whole variety of methods to look at system equilibrium, to look at the effect of strong interaction in disordered system, and also to look at strong interaction at critical point, and even in non-equilibrium in driven system, or to study dynamics and how chaos develop in a quantum system. So one question I've been particularly attracted to and have been playing with is actually it came out from a quantum information, quantum computing problem, actually. People were asking how to build a memory for a quantum computer. That is, how to build a hard drive once we have a quantum computer. So it turns out that even though for quantum computing, at least we have a very well-developed theory for how to do it, and there are, of course, experimental developments that needs to be done. But for quantum hard drive, we don't. There was not a very good proposal, and until about 10 years ago, actually, there was a student of Zhang, a graduate student here, who proposed a three-dimensional model, which made a big breakthrough. And it turns out to be a condensed matter model, what I call a strongly interacting quantum many-body model that nobody has thought of before. That it totally broke our imagination about what kind of gap phases we can have. So that's something that attracted me recently. So it started, of course, in the quantum information regime, and a lot of early studies was in the using the quantum information language, using quantum information tools. But then over the years, it started to get into the condensed matter side, and that's what I found most exciting, that we're starting to think of it not as a purely mathematical problem, but instead in a more physical sense about, for example, how to characterize the phase and how to characterize phase transitions, how to study dynamics and things like that. So, so it turns out that recently we have realized that a lot of these exotic properties that made this particular model used for as a quantum hard drive is very similar to just stacking layers of quantum halls. So just to make connection to the usual experimental system. And then we have been very familiar with quantum Hall system, and as you talk about, you can stack them and make a double layer. But just imagine that if you keep stacking it, and imagine that you make a three-dimensional model out of it. And for this kind of system, it turns out that we don't even have a very good theoretical framework to describe the kind of phase, the kind of universal property, the kind of transition that happens in it. Because in this kind of system, you can imagine that when you stack it, and if you take out one layer, you'll still pretty much have the same order. Right? So we're going into a totally new regime where we're studying intrinsic three-dimensional orders in the presence of arbitrary two-dimensional layers. So that's somewhere we're getting into. So right now, we're of course at a very preliminary stage. We're looking at toy models. We're trying to understand what do we mean by phase. We're trying to understand what is universal property, how to compare whether two models are in the same phase. And finally, maybe one day, we'll be able to get back to answer the question, for example, how to realize it in experiment, how to actually make a good quantum hard drive in order so that people can buy when you have a quantum computer.
Okay, wonderful. Thank you very much, Shia. Okay, so last but certainly not least, Allan.
Very quickly. So first thing I'd like to say is I'm a materials guy too. And so one thing I would like to mention is the quantum Hall effect. Quantum Hall effect has taught us many, many things over the years. We heard from Duncan a beautiful talk on ways to think about the quantum Hall effect. This may be partly a psychological profile, but I frequently fall down a rabbit hole and start thinking about the quantum Hall effect and thinking about these kinds of pictures of understanding the fractional quantum Hall effect, composite fermions, composite bosons, and I always feel like we're just on the edge of saying these things in a more precise way. And that's the rabbit hole I fall down to no good effect every time it's happened so far. But I had the feeling, and I think this came up in Duncan's talk as well, that both from cold atom systems and from going back to materials again, the surprise that we can make wonderful artificial periodic systems using Moiré patterns based on two-dimensional materials, that we're going to have new systems to think about fractional quantum Hall observations. And I think this will give us a new idea, a new opportunity maybe to see things in a new light. So that's one thing I'm very, very excited about. Other thing I would like to say is applications. Our subject ultimately rests on doing something wonderful for the world. So perhaps maybe a wonderful thing that might happen not at some point, not too long, is really building quantum computers. But I think there are other things too, like, for example, green technology challenges that our community can bring to bear on. And another application that maybe is related to green things is Spintronics. I want to say a little thing, just a couple of words about that. So Spintronics is really in this space that Joachim mentioned about non-equilibrium manipulation of quantum states. So in Spintronics, there's one of the main activities now is understanding how transport currents change magnetic states. That's a non-equilibrium manipulation of a collective magnetic state. And the usual language people use to talk about these things talks about spin currents and effects like spin Hall effects. And this language cannot be completely correct because spin is not conserved. And this is particularly true in what are perhaps the most promising materials for spintronics, which are basically topological materials where we have surface states where spin degeneracy is completely lifted, and yet these effects we know from Kang Wang's experiments and others are more strong in those materials than in any other. And I think the ideal material for a spintronics device is a room temperature surface of a topological material, a quantum anomalous Hall effect system perhaps. So I hope we'll get there before too long.
Okay, wonderful. I wish we had a lot more time, but unfortunately we are facing severe time pressure. So let's thank our panelists once again. And we'll have plenty of time for further discussions over dinner, I guess.
That's the last time you let me go first.